Hello, this is the next video in a playlist that I'm calling Generalized Linear Models. In this video, we're going to look at complementary log-log regression. And I'm calling it part 1 because we're going to do a part 2 where we illustrate all these methods for iteratively reweighted least squares in R. We're going to copy these equations exactly and run it and then compare it with the built-in function GLM in R. And in here, there's a very subtle point that I think is often missed when you do complementary log-log regression. So, background videos, of course, look at the playlist, Generalized Linear Models. We're going to follow many of these videos. BV2, the derivative of the inverse trig functions. Here we outline how to take derivatives of inverse functions. Of course, weighted least squares regressions, because we're doing iteratively reweighted least squares. And BV4 is the exponential family, specifically the Bernoulli distribution. In there we derive the means and variances generically using the exponential family and properties from the exponential family. We introduce what's called a log partition, and we take the derivative of it and the second derivative, and it has some nice properties. And we look at those properties in the second video in this playlist. In this video, we're going to, of course, do C log-log, complementary log-log regression. But there it assumes that we use the Gumbel distribution, which is part of the extreme value distributions. I think this is type 1, and as soon as I say that, I could be wrong, could be type 2 or type 3, but I'm pretty sure it's type 1. And we're not going to really discuss the properties of this distribution, but this is what they use. The general CDF is this, and the density is this, and U, mu, and sigma are parameters, but it's not the mean, and that's not the standard deviation, but those are the general parameters. So this is like a location parameter, and that's a scale parameter or a shift parameter. The CDF can be shown to be this. When you're doing this transformation, you let y equal this e function, and then it makes the transformation quite easier. R uses the standard Gumbel distribution. That means mu is 0 and sigma is 1. When it does, it's iteratively reweighted least squares regression. The mean of this Gumbel distribution, or a random variable that follows a Gumbel distribution, is mu plus sigma gamma, and that's the Euler-Mascheroni, if I'm saying it correctly, constant, 0.5 something. The variance can be thought of as pi squared over 6 for the standard Gumbel distribution. So here's the general development for, I'm just going to call it C log-log for complementary log-log regression. And we let y be a continuous random variable. And then right there you're going, wait, but isn't C log-log regression for dichotomous, 0, 1 random variables? Yes, it is. But this is the general development for it. And we're going to let x be covariates that influence y. And we're going to assume y is this linear relationship. It follows this linear combination of our covariates plus some error term, where error is the epsilon is the Gumbel distribution for some mu and sigma. Then what we do is we dichotomize y, call it y star, and it's a 1 if y is greater than c, and it's a 0 if y is less than or equal to c. Now here's a note that when we looked at the probit and the logistic regression, and we did this derivation, we let y star be 1 when y was less than or equal to c. And here we're doing the opposite. So in a sense, we're modeling it backwards, and you'll see what I'm saying, that we're modeling the complement, hence the complementary log-log regression. So the mean of y star, we're going to call it p, which is the expected value. which is the probability that y is equal to 1, right? Because expected value is 0 times the probability of 0, 1 times the probability of 1, so you just get 1. But that's the same as y being greater than c. But y was this, so we plug that in. That's still greater than c. We subtract the linear combination of our covariates to the other side. That's this. Now this next step is, since epsilon is a gumbel with some mu and some sigma, well, it turns out if you subtract mu and divide by sigma, you get the standard gumbel distribution. And I think that's why they use mu and sigma. But that's not the mean, and that's not the standard deviation. And then if you do it to this side, you have to do it to every variable over here. But now here, so this linear combination, we take the beta 1 and combine it with the c, and then the mu that we just subtract, we keep them together, and of course we're dividing by sigma. And then every other covariate, beta, we write like this. Now, this can be generically called beta 0, and if we take that negative into this, these parameters here, and just reparameterize it, call it beta 1 star, and we keep going all the way to beta k star. This side can be written as a linear combination of our covariates like this, and where x is the standard gumbel distribution. Now, since this is the probability of being greater than some number, that's the 1 minus the CDF, or the survival function. Okay, so now we have P modeled as 1 minus, F, capital F of this linear combination. Now, to solve for this linear combination by itself, we need to subtract it to the other side, take the P back to this side. So now we have capital F of 1 minus P. Then we take the inverse of F, and F is a CDF, so it's strictly increasing on this continuous variable. And we get this, right? So F was over here, we take the inverse, and actually it leaves this. But on this side we had 1 minus P, and that's the inverse. And 1 minus the mean. And anyway, this transformation is called complementary log-log regression, or log transformation. Now, let's look at that in a little more detail. So the CDF was this, and so the inverse function is this. And the way you get an inverse, you make that x a y, and you call this x, and then you solve. So you take the log of both sides, and then you have to take the minus, then you take the log, and then you take that minus to the other side, and that's what this is. And that minus right there is so important, it's very important to actually fully understand what's going on. Now, in everything that I've ever looked at, that minus is left off. And on page 4, we'll go into much more detail why it's left off and what we're going to do about it when we're using the iteratively weighted least squares from scratch. Okay, so now the density of our new variable y star is a binomial. It's either 1 or 0. And so this is the probability of a 1, right? It's that we're greater than some constant, which ended up being 1 minus this capital F. And then probably to 0 was the CDF. Okay, now that's this is the density is like the likelihood, but we switch the y and the b, and we just thinking about it differently. But this is for 1y, so the joint would be the product of all these, and then the log likelihood. And we're skipping a few steps because I think if you made it this far, you understand that. So the log likelihood, we'll call it L, which is the log of the likelihood, and these are vectors because we're doing it for, not that y is a vector, and because we're doing it for all of our data, which ends up being the sum. So if you take the log You know, that y can come out front and it's the log of this. That can come out front and it's the log of that. Well, and you maximize it. Boom. We're done. And this is what they did to find the beta estimates. But 50 years ago, when generalized linear models were discovered, then I think it brings a much more robust approach to solve for these betas. And that's what we're going to use. And we're going to follow the fourth video in my playlist. It's called Generalized Linear Models, Iteratively Reweighted Least Squares for a General Link. And I would refer to that if you haven't watched it, because we're going to follow it exactly. Okay. So here now the likelihood or the density of a value is this. This is a binomial. A Bernoulli density in log or exponential form. And I would say CBV4 for that. This piece right here is called a log partition, plays an extremely important role in generalized linear models. I would see the second video on my playlist for that. So to come up with the likelihood, we have to sum all these, or it's actually the product, and then we take the log, which is a sum, but the log and that e go away, so we get the exponent. Anyway, that's what we do. So when we're going to maximize this, we're going to do it for one Li, and then we're going to do the sum later. It just makes the derivations much easier. So now we need to maximize this in terms of betas, but there's no betas here. So we're going to have to use the chain rule somehow. Okay. So first of all, this is in terms of theta. So let's just take the derivative in terms of theta, and we get this. So that's y. And the derivative of the log partition is the mean, and CBV4 for that. But on page 1, we said the mean was 1 minus the CDF of this linear combination. That's what we did on part 1. Now, eta is our linear combination. So the derivative of eta with respect to beta j, you'd find the beta j and take its coefficient, which is xij. Now, here, the pi, the mean of our data, which we can generically call mu I, is the derivative of this log partition right there. Okay, that's what it is. So we can generically call this b. It's a b of theta. It's a function of theta. So we take the derivative of this, and that's the mean of our value. It's actually pretty cool to go back and watch BV4 to derive that. So the variance of y, which we know is p times q, or p times 1 minus p, but p is the mean, so we can write it mu I, 1 minus mu I. And there we generically call that the variance function, which ends up being the second derivative of the log partition. Another reason to see BV4 and how that's derived. So now to take the derivative of theta with respect to mu I. So, but theta is not solved by itself. So if we take the inverse of that, then theta is by itself, and then it makes the derivative much easier. But BV2, you can, since we're doing inverses of each other, you can look at that video and discover that it's really 1 over the reciprocal of this. And then the partial of mu I with respect to theta I is easier. You just take this, the derivative of this again, which is the second derivative, which is the variance function, which is what this is. So the variance function was mu I, 1 minus mu I, but we said mu I was 1 minus f, and that makes 1 minus mu I, just capital F, the CDF, and that's the Gumbel distribution. Now, f prime, or not f prime, f inverse of 1 minus mu, and actually that's the complement in the complementary log, is we're saying that's a linear combination of our covariates, right? But we can take f to both sides and then solve for mu I, and we get this. Now the derivative, the partial of mu I with respect to eta I, that's constant, so it goes away, and the minus is out front, and then derivative of the CDF is the density evaluated at A to I. So this is it. Remember, that's a Gumbel distribution, standard Gumbel distribution. And then of course eta is the linear combination. Now we take all those pieces and we put them together. Now ultimately we want the derivative of our log likelihood in respect to beta j. This is an easy one because our likelihood was in terms of theta. The eta is in terms of beta, so that's an easy one. Then we had to find these so those cancel, leaving just this. Now when we put these pieces in, this one is this first piece here. That was the denominator. This was the minus the density. And this is the xij. We set it to 0 and solve. And we're done. But that's not as easy as it seems, and that's why they introduced the iteratively reweighted least squares regression. So step 1 is to estimate the betas to just be 0. We have to pick some value, so make them 0. Now step 2 is we have to come up with values so we can run this weighted least squares regression and find beta hat. And so if we let eta be our linear combination, and mu was 1 minus the CDF of eta, and then we're going to let z be the linear combinations yi minus mu I times the derivative of our link function. And our link function was, the inverse CDF of the Gumbel. But the derivative of g is 1 over the derivative of the g inverse. And g inverse was the 1 minus capital F of eta, or of mu, I mean. So that's how we get the 1 over the minus the density of mu I. So that's what we plug in right here. Remember, the mu is 1 minus this. Okay. So now the weight is, this is the formula that we used in the fourth video in the playlist. And then this we discovered was this, and so we have to take the reciprocal. But when you're squaring something, we can get rid of that negative out front. Variance function is mu I 1 minus mu I. Then all this we know, we just found z and we found w, which are the weights here, and we come up with an estimate of beta. And then we just start the whole process again, maximize it, do them, and we just keep repeating until convergence, until each estimate of the betas get closer and closer to within some tolerance. Now this is so cool, we're going to take these exact equations, literally these exact equations, copy them into R and run it and compare it with the built-in function, and we're going to get 100% the same thing. But here's a big note, and a big note that you don't see in the literature, and it's in my mind it's so underappreciated that I think it's worth pointing out. So in GLM we take our link function and of the means, and we get a linear combination. And here, but we're going to do 1 minus the mean, the complement of the mean. Then that's the generalized linear models. Now, what we just derived was this. Remember, we took the inverse Gumbel distribution. That's this, right? And so we're modeling this, and that's what we'll come up with, these beta estimates, right? But what is done in R is they model this. So they take that minus and put it in there and then model it. But what is crazy in my mind is that no one describes it like that. They just say xi beta I. But if we were to model this and this, it would be, the betas would have opposite signs. And so really they're modeling the minus the beta. And I'll even point that out a little more. So the CDF of a Gumbel is this, right? So then the inverse CDF is this. we did that on page 2, right? So this is it. And so if we model this, like every website, every book, every R thing always models it like this. This is the way they describe it. Okay, so now let's take the E to that, and then take the minus, and then take the E, and we're right here. Now, is this the Gumbel CDF? Sort of, but this is different. So where's that minus? So really, the minus and then the minus beta. Okay, so when R solves this, they're incorporating that minus already. And it's not obvious. And so I think that's so underappreciated. So now what do we do? How do we handle it? There's really 2 approaches. That in the approach that I use, we can just add a negative to the beta after convergence so we can match R and every other software. Or we can multiply the data matrix just by -1 and then run it. And we'll come up with what R has. And we'll illustrate both of these in R and to make sure that it's fully understood. But that darn negative is so underappreciated in my mind in complementary log regression. Well, anyway, that's all I have for today. I'm going to jump into R for the next video to illustrate these. Hope you liked that. I sure did. Please subscribe so you don't miss the next video. Thanks a lot. Bye.